On this program, speed, how vertebrates are able to actualize it, its effects on the human body, and the aerodynamic principles that help optimize it. The quest for speed dates back to our most remote ancestors. In order to survive, prehistoric man often had to flee, as fast as he could, from predators a great deal better equipped in horns, fangs, and claws. Vertebrate locomotion at low and high speed depends, we are inclined to forget, on a skillful orchestration. The mobility of animals is a sort of super function. It is key to their survival and diversification. By moving about, they can find more food and avoid depleting their immediate environment. They can escape from predators or stalk their prey. They also often have to travel to find a sexual mate. Indeed, in many species, the males and females live apart, coming together only at mating time. So over the course of evolution, almost all the families of vertebrates have undergone adaptations to make them swifter. Speed of motion depends essentially on two factors: the length of the strides and their frequency. The frequency is defined by the number of strides per unit of time. In practical terms, this means that a long-legged animal can take big strides, which gives it an advantage in terms of speed. But for an animal to be fast, it also must be able to move its legs from one point of ground contact to the next very quickly, which enables it to attain a high frequency of movement. Small animals, such as rodents, can also get about very quickly, because even with their short legs, the frequency of their movements is very high. In addition, given their light weight, their inertia is very low. In all vertebrates, the legs cyclically perform two main movements: lift, during which the leg leaves its contact with the ground to go to another contact point farther away, and set down, during which the foot remains in contact with the ground while the body moves forward. The motion of a horse provides a good example of these cyclic actions. When a horse trots, its four legs move in a given order. The trot is a symmetrical diagonal gait in which diagonal pairs of legs move forward together. To increase its gait, the horse reduces the number of contact points with the ground for a given time. The gallop is a 3-beat gait, faster than a canter, in which all of the horse's 4 feet are off the ground at the same time during each stride. The horse goes from trot to canter to gallop by throwing one of its forelegs forward sooner than it would for a trot. An animal's speed also depends on its anatomy. Four-legged animals well adapted to running have thin legs whose muscles are joined at the base of the leg. This morphology enables quadrupeds to overcome the inertia peculiar to each of its legs. For example, of all the cats, the cheetah has the lightest legs. It thus beats the record for top speed. The cougar, on the other hand, whose legs are heavier, is far less swift. As for the elephant, due to its imposing mass, it moves very slowly. Its bones are massive, and its leg segments are arranged in columns to withstand flexion and crushing. The elephant ambles along, moving both legs on the same side at the same time. Its pendulum-like motion allows it to restrict the effect of inertia, but naturally prevents it from galloping. Physiologically, speed requires a considerable expenditure of energy. This energy is chiefly measured by the amount of oxygen the muscles consume. Depending on the speed strategies, the muscle fibers of vertebrates are either slow or fast contracting. Animals belonging to the Canidae family, the sled dog, for instance, have good stamina. Although sled dogs never attain great speeds, they can run all day long. Their slow muscle fibers are fatigue resistant, and they consume energy regularly. Sled dogs therefore compensate for their lack of speed with remarkable endurance. Other members of the Canidae family, wolves, are able to catch, simply by wearing them down, prey that is faster but whose muscles tire more quickly. The cheetah, however, a top-notch sprinter, is only able to run short distances, 200 meters, flat out. Its fast muscle fibers consume no oxygen during the exertion. After running at top speed, a cheetah is completely asphyxiated. It has to stop to eliminate the toxins produced. That's why it gets as close as it can to its prey before pouncing in a lightning attack. Humans, too, are well adapted for running. Our morphology enables us to take long strides at a relatively high frequency. In addition, our muscles give us good stamina. However, energy-wise, the reciprocating motion of our feet is a constraint. Each time we set a foot down, it slows us down, and we have to re-accelerate, which means expend energy. In biology, compromise is the rule. The ideal situation would be to have countless legs. This would reduce the constant impacts of reciprocating motion. Coordinating such a system would, however, be a problem. Acceleration? Impossible, except at the risk of getting our legs completely tangled up. The increase of speed has always had a major impact on the world. The car relegated the horse to the racetrack. Planes, trains, subways have trivialized running. Rockets and boats rip through air and water at speeds unimaginable just a century ago. On a purely physical level, acceleration also has unexpected effects on the human body. Humans are insensitive to speed. It may seem hard to believe, and yet living on the Earth's surface, we are subjected to constant motion. Just think, not only does the planet itself rotate, it also revolves around the sun. Yet we have no sensation of these movements nor of their speeds. Sitting or standing, our impression is one of immobility, which is not the case since the Earth, which rotates at over 1,000 kilometers per hour on its axis, spins us along with it. While we're insensitive to speed as such, we are sensitive to variations in speed, to acceleration, for instance. A striking example of acceleration is a fighter plane's catapult launch, or takeoff from an aircraft carrier. These takeoffs require tremendous acceleration. In flight, the combat maneuvers, aerial acrobatics, and sudden changes in course also subject the pilots to considerable forces of acceleration. In aeronautics, such accelerations are expressed in gravity, or G numbers. A pilot weighing 150 pounds, or 70 kilograms, flying a plane that requires an acceleration of 6 Gs to change course, for example, will be subjected to an acceleration force equal to 6 times his own weight. It's as if he suddenly weighed 420 kilos, almost 1,000 pounds. Accelerations like these interfere with the organism. Our bodily fluids, such as blood, will, in a manner of speaking, suddenly weigh 6 times their normal weight. For the heart, which sends the blood through the body, it becomes the equivalent of stirring a liquid which has the density of iron. insufficient circulation in the upper part of the body, especially in the brain, causes disorders in sensory perception. For a mean acceleration of 4 Gs, a lack of circulation to the brain and eyes triggers a first warning sign: gray out. In a gray out, color perception and visual acuity are diminished. The peripheral field, that is the viewing angle, narrows. It's a little as if the pilot was speeding through a tunnel filled with fog. Gray outs occur frequently. It is an alarm signal warning the pilot of his limit of tolerance. Indeed, if the acceleration increases, if only by 0.5 Gs, blackout occurs with a total loss of vision. Fortunately, both these phenomena subside as soon as the acceleration stops. After a blackout, if the acceleration increases another 0.5 Gs, the pilot may lose consciousness. Loss of consciousness can also occur without warning. It is often accompanied by convulsive movements, and it does not recover immediately with deceleration. Before the pilot fully regains consciousness, he will go through a stage of disorientation in time and space. At worst, it may take the pilot up to 1 minute and 20 seconds to regain consciousness, and in a fast-traveling plane, that can have tragic consequences and may explain some accidents. To minimize the effects of acceleration, pilots wear anti-G pants. The anti-gravitic suit, inflated with compressed gas, exerts pressure on the lower part of the body, thus restabilizing the circulation in the upper body. For testing and training, researchers and staff use a centrifuge. Part of this device, the pod, contains a plane seat on which the subject sits. The pod swivels and is subjected to the same acceleration as a fighter plane. A video camera and voice communication ensures an ongoing contact with the control room, where the data is recorded and where the subject's cardiovascular activity is also monitored. The amount of oxygen in the blood, which varies according to pressure, can also be measured. As can variations in the visual field experienced under grayout. The pilot can at all times press a button to halt the experiment. Otherwise, another pressure sensor system will detect the subject's loss of consciousness if his hand suddenly goes limp. Of course, researchers continue to try to reduce acceleration's disabling effects on pilots. However, in spite of their efforts, the fact remains that it's the pilot's own physical resistance that limits their tolerance of powerful accelerations. Aviation medicine often relies on the centrifuge to conduct its experiments, and wind and water tunnels are the routine tools of aerodynamics. Aerodynamics is the science which deals with dynamics of bodies moving relative to gases, especially the interaction of moving objects with the atmosphere. It plays an instrumental role in ship and automotive design, but also in the design of such stationary structures as bridges and towers, subjected to the pressures of the winds. Aviation greatly benefits from the background knowledge in this field, whether it's to increase the speed or maneuverability of an aircraft, or to make it more fuel efficient. Aerodynamics helps to determine the optimum shapes for achieving the objective. Planes fly even though they are heavier than air. The wings, or wing system, are what mainly sustain a plane in flight. Airplane wings have a downward curvature. Viewed in profile, a wing's curve is more pronounced on top than underneath. In flight, while air streams over both surfaces, it flows at a faster rate over the wings than under them. Indeed, due to that curvature, at any given time, the air molecules cover a greater distance above the wing than below it. Above the wing, the molecules of air move away from each other, whereas under it, they stick together or move closer to each other. The air pressure higher under the wings than above them, therefore pushes the plane upward. That vertical aerodynamic force is called lift. When the lift is equal to the weight of the plane, the latter maintains its altitude. If the lift exceeds the weight of the plane gains altitude. Conversely, if it is lower, the plane loses altitude. A plane's wing system is subjected to another force, this one horizontal, called drag. Drag opposes the plane's motion. The thrust of the engines is what overcomes that resistance. Aerodynamics specialists' primary objective is therefore to design and develop wing systems whose forms will reduce a plane's overall drag. A modification to the sweepback, for example, that is the angle of the wings relative to the fuselage, can increase its speed. Enlarging the sweepback angle will delay shock waves, which are the waves the plane makes when its speed approaches and exceeds the speed of sound, and which generate further resistance. So the greater a plane's sweepback, the greater its cruising speed. As for helicopters, their flight is assured by rotary wings. This wing system both sustains the aircraft in the air and propels it forward. One or several large diameter propellers, the rotors, activated by an appropriate engine system, produce the aircraft's lifting force. At takeoff, the rotor blades rotate parallel to the ground. This provides little lift. The pilot then tilts the leading edges of the blades upwards. The airflow is then faster over the blades than under them. As a result, the pressure above the rotor blades decreases, thereby creating an upward suction force, lift. Engine acceleration also increases the lift. One of a helicopter's greatest advantages is the ability to hover. Hovering is achieved thanks to a small rotor attached to the tail of the aircraft. Without a tail rotor, a thrust counter to the circular motion of the blades would cause the helicopter to spin in the opposite direction than that of the main rotor. This small rotor creates a sideways thrust that opposes such movement and ensures the helicopter's stability. A helicopter's maneuvers are mainly produced by the inclination of the circle described by the main rotor blades. If the circle is horizontal, the lift will be vertical. When the pilot tilts the rotor circle forward, the helicopter will move in that direction. To skid, that is to veer left or right, the pilot tilts the rotor circle in the direction he wants to go. He does the same to make the aircraft go backwards. A helicopter's main drawback is its wing system. Its rotary wings limit it to maximum cruising speeds of about 400 kilometers per hour. Beyond that, the level of vibration as well as air resistance become too great. By refining the silhouette of helicopters, aerodynamic designers hope to be able to improve their speed. To see how a prototype will perform, researchers use computer simulation techniques. They frequently work with simple shapes in order to understand the basic aerodynamic phenomena. Wind tests are also used to validate their computations. These tests consist of fastening a model aircraft inside a duct through which air flows at a selected speed. Sensors placed inside or near the model aircraft transmit their data to a computer. Researchers can then calculate the model's lift and drag and compare the results with the numerical simulation. If they want to visualize the airflow or slipstream, researchers can, among other techniques, use the hydraulic analogy. Indeed, below speeds of 200 kilometers per hour, water reacts much as air does. A model toward which liquid colorants are routed is subjected to a stream of water of specified speed. The liquid colorants, whose densities are different from that of water, reveal the slipstream and wake to be analyzed. It is in the aerodynamics laboratories that the aircrafts of tomorrow are being shaped. The last century was the century of speed in real space. The next will be the century of the instant in virtual space. No need to travel at high speeds anymore, thanks to electronic helmets, gloves, and suits. We will be able to be where we are and somewhere else at the same time.